Welcome back to multivariate calculus. In this video, we're looking at volume integrals in other coordinate systems. When we were studying area integrals, we came across this idea called the Jacobian that allowed us to generalize our coordinates. Here, I want to take that same thing and generalize it into 3 dimensions. So let me get my head out of the way so I can do just that. For an area integral, for the area integral Jacobian, if we had coordinates as x and y and we wanted coordinates as u and v, we had that thing partial of x and y over partial of u and v given as the determinant of the matrix partial x partial u, partial x partial v, partial y partial u, partial y partial v. And we took that determinant of that 2 by 2 matrix in order to find our change of coordinates so that dA was this Jacobian dV du. And the way that the Jacobian worked, in the numerator, x and y defines the rows of the matrix. So partials of x, partials with y. And the denominator defines the column, partial with respect to u, partial with respect to v. And if we just take that and extend it from 2 to 3, we will get a Jacobian in 3 dimensions that works just as well. So we can have a volume integral Jacobian, which will have partial of x, y, and z over partial of u, v, and I guess w. So we need the partial of x across the first row. We're going to take partials of y across the second row. And we're going to take partials of z across the third row. In the first column, we're going to take the partial with respect to u. In the second column, we're going to take the partial with respect to v. And in the third column, we're going to take the partial with respect to w. And we will get that our dv is partial of x, y, and z over partial of u, v, and w, dw, dv, du. So it's the same thing, just extended out into 3 dimensions. And where else should we go with this but to the coordinates that we already have some familiarity with? In cylindrical coordinates, x of r, theta, and z is given as r times cosine of theta. Y of r, theta, and z is given as r sine theta. And z of r, theta, and z is just, well, z. Nothing too crazy happening there. And so my Jacobian, partial of x, y, and z over partial of r, theta, and z is going to be partial of x with respect to r is cosine theta. Partial of x with respect to theta, well, the derivative of cosine is minus sine, so we'll have minus r sine theta. And partial of x with respect to z is 0. Partial of y with respect to r is going to be sine theta. Partial of r sine theta with respect to theta is r cosine theta. And partial of that with respect to z is 0. All right, partial of z with respect to r is 0. Partial of z with respect to theta is 0. Partial of z with respect to z is 1. And expanding this down, there's a trick in linear algebra that lets you expand down other rows and columns. If you've seen that before, this is going to be a lot easier than what I'm going to show you. But if you haven't seen that before, I'm just going to continue on my expand across the first row. So we're going to have cosine of theta times the 2 by 2 matrix if we eliminate first row and column, which has r cosine theta 0, 0, 1, minus, a minus is plus, r sine theta times the determinant of the 2 by 2 matrix if I eliminate that row and column, which is sine theta 0, 0, 1, and then my third entry in the first row is 0, so it doesn't matter what the matrix is because I'm going to multiply it times 0 and I'm going to get 0. All right, but I got r cosine theta times 1 minus 0, which is just r cosine theta. I've got sine theta times 1, which is sine theta, minus 0, which is still just sine theta, and then my plus 0, which goes away. And in cylindrical coordinates, the Jacobian is r. And that should look familiar to you, because in area coordinates, we know that in polar coordinates, dA is r, dr d theta. And what we just discovered is that for cylindrical coordinates, dv is r, dr d theta, and just an extra dz. All right, so once you remember that from your area coordinates, you can extend it into volume coordinates, and it's really no change at all. Right. Because we've spent so much time thinking about area integrals in polar coordinates, I don't want to spend more time here today thinking about volume integrals in cylindrical coordinates. The conversion is so similar. Z stays the same, X and Y get treated the same way they did before. It's really nothing new. Let's go onward and look at the other three-dimensional coordinate system we've talked about, spherical coordinates. In spherical coordinates, we know that x as a function of rho, theta, and phi is given by rho cosine theta sine phi. Y as a function of rho, theta, and phi is given as rho sine theta sine phi, and z as a function of rho, theta, and phi is given as rho cosine phi. And so we can set up our Jacobian the same way we had previously, partial of x, y, and z with respect to rho, theta, and phi. And I'm going to try to write this as small as possible so that everything fits and I can keep working along. But partial of x with respect to rho will be cosine theta sine phi. Partial of x with respect to theta will be minus rho sine theta sine phi. And partial of x with respect to phi will be rho cosine theta cosine phi. Partials on y, we will get sine theta sine phi. We'll get rho cosine theta sine phi, and we'll get rho sine theta cosine phi. Partials on z are going to give us cosine phi 0 and minus rho sine phi. As with the cylindrical coordinates example, if you've studied linear algebra in the past and you know how to take determinants by expanding on other rows or columns, expanding on the third row is going to make this a lot nicer. I'm assuming that you've not seen that before, so we'll just expand on the first row the same way we always do. We've got cosine theta sine phi times the 2 by 2 determinant, which will be rho cosine theta sine phi, rho sine theta cosine phi, 0, and minus rho sine phi. We've got minus and then a minus in the problem, so all told that's plus rho sine theta sine phi times the 2 by 2 determinant sine theta sine phi, rho sine theta cosine phi, and minus rho sine phi. And then we've got the last term, rho cosine theta cosine phi times the 2 by 2 determinant sine theta sine phi, rho cosine theta sine phi cosine phi, and 0. All right, so expanding those out, in the first row, we have cosine theta sine phi times rho cosine theta sine phi times minus rho sine phi is going to be minus rho squared cosine theta sine squared phi. In the second row, we're going to have rho sine theta sine phi times sine theta sine phi times minus rho sine phi is minus rho sine theta sine squared phi. And then we'll have minus cosine phi times rho sine theta cosine phi is minus rho sine theta cosine squared phi. And then in our third row, we have rho cosine theta cosine phi times, well, 0 minus rho cosine theta sine phi cosine phi. That's a little bit of a mess, but so we have it. All right. And from here, we want to start trying to simplify and clean things up. And as we've seen in previous applications, we're going to pretty quickly find some really nice things with Pythagorean identities. Right here, I've got the same thing being multiplied by sine squared phi and cosine squared phi. So something times sine phi plus the same thing times cosine squared phi is just that thing. And I'll leave the first bit the same. That second bit is now rho sine theta sine phi just being multiplied by minus rho sine theta. And the third bit is just going to stay the same for the moment. before I take the time to expand these things together. So cosine theta times cosine theta. I'm going to leave that a little bit weird. I'm going to have that as sine phi times sine squared phi, because again, I have the Pythagorean identities in my mind, and I'm kind of hopeful that that sine squared phi is going to find a cosine squared phi to become good friends with later on. And then we'll have, in this second term, is going to be rho squared. I guess we've got sine squared theta, and we've got sine phi. And in the third term, we've got rho squared, we've got cosine squared theta, we've got sine phi, and we've got cosine squared phi. And what is that, precognition or something, or just knowing what's supposed to happen? I've got this rho squared cosine squared theta sine phi showing up in two places, being multiplied by sine squared phi and being multiplied by cosine squared phi. So using the Pythagorean identity, those are going to collapse. And we'll have minus rho squared cosine squared theta sine phi. And then the other term that's left is rho squared sine squared theta sine phi. And hey, one more time, we've got a rho squared, we've got a sine of phi. We've got another rho squared and another sine of phi. We've got a cosine squared, we've got a sine squared. Those things are going to collapse one last time. Minus rho squared sine phi. And so in spherical coordinates, dv is minus rho squared sine phi d rho d theta d phi. Normally at this point, I would go through an example and show you why this is useful, but this video is already running fairly long. So I'd actually like you to take a look at this problem on your own. We're going to take the triple integral for a function f of x, y, and z equals x squared plus y squared plus z squared. And the region of integration is the unit sphere, the ball where rho is less than or equal to 1. All right, so take a couple of minutes, see what you can do with that integral, and I'll see you in the next video.